Hello everyone, my name is Dr. Deepak Yadav, and today we will discuss a complex topic of unit number 5 of antenna and wave propagation subject, that is skip distance. As we already do two lectures over this wave propagation, in which we study the ground wave propagation and space wave propagation, and there is another thing. There is the wave that is known as a sky wave propagation, in which a point that is arise that is known as skip distance. Then we will discuss this skip distance, what is this skip distance, and how this will tackle while there is a communication from the transmitter to the receiver. So this is the topic of sky wave propagation, in which the skip distance is the distance, that is the minimum distance that is not covered by the transmitter, when the reception of the sky wave. The sky wave is actually the wave that is reflected from the layers of the ionosphere. As we already discussed in the previous lecture, the ionosphere is made up of different layers like D, E, F1 and F2 layer. And when the wave of particular frequency, which is already discussed in the previous lecture, that it enters at the different incident angle, it get reflected back by the ionosphere due to the very large concentration of electron in these layers. So as as we can see, there is a multiple wave that is reflected from the ionosphere. Like in case of ray number 4, when it is incident at an angle I4, the incident angle is so high that the wave is not reflected by the ionosphere, but it penetrates the ionosphere and goes into the sphere. And again, if we decrease the some incident angle, like for the wave number 3, it get little reflected, but the amount of reflection is not so much high, that is the total internal reflection take place and the wave penetrate into the sky, into the space as well. In case of third, the incident angle is such that the wave is get reflected, it penetrate into the ionosphere up to some instant and then get reflected back by the different layer of the ionosphere and goes and receive at the receiver. So this is the minimum angle by which the wave is get reflected back from the ionosphere. So this angle is known as incident angle, and the distance that is not covered by this I2 angle, that is skip distance, this zone is not covered by this distance. So as the ionosphere is very high in the height, like 15 to 7 like 50 kilometer, so this zone is almost 30 to 35 kilometer, that is not covered by the transmitter by the sky wave propagation. So this zone is also known as dead zone or skip zone or skip distance, which is not covered by the minimum angle of incident of the wave by the ionosphere. The frequency used at which this minimum distance take place, that is known as maximum usable frequency. So there is also a different frequency, as we already discussed, like critical frequency, maximum usable frequency, and this communication where skip distance is measured is known as the frequency is known as maximum usable frequency. If again we decrease the angle, like for this wave, the it again reflected back from the ionosphere, even from the lower layers, and reaches to the earth. But this distance is now increased. It is increased from A to this point, and this skip zone is increased as we increase the incident angle or change the frequency. So the minimum distance over which we cannot do the communication in the dead zones, these are from A to this point B, and this is known as the skip distance. So this is the skip distance for the minimum incident angle and maximum usable frequency. And this zone is known as skip zone, because in the skip zone, even it is very much nearer to the transmitter, the signal is not received, because the signal goes into the space and reflected by the ionosphere. And due to this scenario, the large amount of the area which is near the transmitter is not covered by the sky wave propagation, in which we use another method to communicate, like ground wave propagation, like in this figure. if we want to try to cover the escape distance, we use ground wave propagation. But the problem with the ground wave propagation is these waves are at high frequency and cannot be travel far from the transmitting antenna and goes down. So even for the skywave propagation, we are not able to cover the escape zone. While using the ground wave propagation, we are not still able to cover the escape zone due to the very high frequency scenario. The wave is got like it loses its amplitude. So even with ground wave and skywave propagation, we are not able to cover the complete escape zone. Even this escape distances change by the time of the day. Like in the daytime, the escape distance is minimum, and the night time the escape distance is maximum for the same frequency as well as for the same layer of reflection. The thing is that in the daytime, the sun directly shine overhead over the ionosphere, and the high frequency rays coming from the sun like X-ray, gamma radiation can ionize the air molecules, and large amount of ion is available in the different layer of the ionosphere in the daytime. So due to that, the reflection is very sharp in the daytime, while in the night time, due to the non presence of the sun, the most of the molecule of the air get again combined with the electron, and there is very less concentration of ion available, due to which the reflection goes a little larger time to get reflected, and the escape zone in the daytime is minimum, while in the night time is the escape distance is again increased. So if anyone is receiving the signal over in this zone, in the daytime he or she is not able to receive the signal, while in the night time he is able to receive the signal in this zone. That is the this is the with the help of this diagram we can calculate the use of maximum usable frequency and how it is connected with the escape distance. So if we consider the flat earth scenario, then from A to C is the escape distance, that is represented by D, and this is the layer of the ionosphere by which the wave get reflected. And let's suppose this is the height of the ionosphere, and the incident angle is R and reflected angle is incident angle is I and reflected angle is R. Then this distance is nothing but with the help of Pythagoras theorem, this is under root of D by 2 whole square plus H square. Now if we take the reflection formula, that is the sine of the incident angle divided by the sine of the reflected angle, this is the refracting index of the medium, is represented by mu. And if the incident angle is I, then and it take the total internal reflection, that's why the refractive angle is 90 degree, then sine is equal to 90 degree. The refractive index of the of the ionosphere is now became sine I. And we already discussed this formula in the previous lecture. In that lecture, we will derive this formula with the help of different techniques. And the refractive index is given by under root of the ionosphere layers is given by 1 minus 81 nmx by f MUF, where MUF is the maximum usable frequency over which the escape distance is calculated, and n is the maximum amount of electron present, number of electron या electron density over here. Then sine I is equal to under root of 1 minus 81 n by MUF, and we are also calculated this 81 n max is nothing but the critical frequency, as we put this critical frequency over here, and solve this for the maximum usable frequency. So for the maximum usable frequency, take the square, then 1 minus sine square I is equal to cos square I. Cos square I, then if we want to calculate MUF, take the under root, cos I is equal to FC upon F MUF. But cos I is also represented with this formula, is that is BO upon AB. This is OB upon AB for cos of I. And then cos of I is equal to H upon under root D by 2 whole square plus H square. Or if we adjust this term, sin I is equal to twice of H under root D square plus 4H square. So if we compare these two formulas, then we have this equation, and now we can easily calculate MUF, or even this d is nothing but the escape distance for the flat earth. So you can also calculate the escape distance d for the flat earth, and this is nothing but d escape distance is equal to twice of h. H is the height of the ionosphere, and under root of f MUF, maximum usual frequency, divided by critical frequency of the layer minus 1. So this is the formula of the escape distance. D is equal to twice of h under root of f MUF square upon fc square minus 1. So this escape distance is depend on the layer, on the height of the layer over which layer is used for the reflection, that is height of the ionosphere, maximum usable frequency, and even critical frequency of this layer. The escape distance is now going to be changed as the time changes, because in the daytime this h is for the particular layer, this h is varying from daytime to night time. Even critical frequency is also varying as the concentration of the electron is changed, and MUF is fixed. So the escape distance is directly proportional to MUF by these two and corrected by these two variables. Now if we consider the accurate scenario that that our earth is not flat, this is the escape distance for the flat earth, but we know that the earth is curved, and the distance between the transmitter and the receiver in case of ionospheric reflection is very large. So we cannot like remove or consider that earth is flat. We have to calculate for the curved earth surface. So now we again calculate this escape distance for the curved earth with the help of this this diagram over here. Here the earth is curved, and capital R is the radius of the earth, and O is the center of the earth. So if this is the escape distance d from A to C, and this escaped and this is again R, and this is equal to D. So R is equal to, and this angle, if this make angle theta with the help of radius, then this theta, this is theta, this is R, then this AT is nothing but A sin theta, and this D is nothing but over here is equal to, not D, this is OT. OT is equal to R cos theta, where D this d is nothing but the escape distance in case of curved earth from A to C. So this AT is equal to R sin theta, and OT is equal to R cos theta, and from this is h is the height from the earth's surface from this point to this point. This is I, incident angle is I, and reflected angle is R. This is point E, this is ionospheric layer over which the reflection take place, and A and C points. Now if we take the formula, arc angle is equal to arc by radius. So 2 theta is nothing but this 2 theta this 2 theta is nothing but arc by radius, and arc is equal to our escape distance d, and radius is equal to r, that is the radius of the earth. Then we have the d is equal to 2 into r into theta. Now if we calculate this theta value with the help of different trigonometrical equations, so that AT is nothing but R sin theta, as we see earlier in this lecture, and OT is equal to R cos theta. Then BT is nothing but EB plus OE minus OT, that is OT, this is EB, and this is OT, and this is ET. So what we have calculate? We have to calculate the height of the ionosphere BT. The height of the ionosphere BT is equal to this minus this plus this. So EB plus OE minus OT, that is H, height of the ionosphere, plus radius of the earth minus R cos theta. So this is the equation of BT. Then AB is nothing but under root AT square plus BT square. Again trigonometrical formula over here. AT is nothing but AT square, AB is nothing but AT square plus BT square. AT is sin R sin theta, and this BT is we already calculated. BD is equal to H plus R minus R cos theta. So by putting the values in this equation, we have this scenario, this AB. Again, if we calculate cos of I is equal to BT by AT, BT is equal to H plus R minus R sin theta, and this is under root of r sin square theta plus h plus r minus r cos square theta. Or if we take the square on both the side, we have cos square I is equal to this, and this cos square I is nothing but fc square of over f mu f whole square, and this is equal to this. If we take the under root, then these squares are removed. Or we can calculate cos theta, that is cos I, okay, and this is cos theta is nothing but OA by OB. This is capital R, that is radius of the earth, divided by r plus h. Then if we take some because r is very large, r is the radius of the earth, and it is nothing but 6,400 kilometer in compared to height of the ionosphere. This is only about 50 kilometers. So this 50 kilometer is very less in compared to 6,400 kilometer. So we take some consideration over here for the value of theta. Cos theta is equal to r divided by, from this equation, take capital R common, r by r cancel, 1 plus h by r ki power minus 1. So this h by r is very small, because h is very small, r is very large. Then we take the binomials approximation over here. So due to the binomial approximation, 1 minus h by r, this became the equation 1 minus h by r, as h by r is very less than 1. Or this can also be written as h by r is nothing but sin theta, then cos theta. Okay, cos theta is equal to under root 1 minus sin square theta. This sin square theta, as the theta angle is very small, because skip distance is very small compared to the radius of the earth. So the angle made by this thing, this theta angle, this is very small. So the sin theta is again very small. So sin theta is nothing but theta over here. So 1 minus theta square, and cos theta is equal to 1 minus theta square raised to the power 1 by 2. Or again theta is very small, so we can again binomial approximation over here, 1 minus theta square by 2. So this 1 minus theta square by 2, that is equal to cos theta, is equal to 1 minus h by r over here. And from this equation we can calculate theta square is equal to 2h by r. Now in this equation, d is equal to 2 r theta. If we put the value of theta, that is twice of h by r raised to the power 1 by 2, and calculate, we can find the d is nothing but under root of 8h into r. Now if we take the consideration cos theta is equal to 1 minus h by r, then 1 minus d square by 8r square. Then sin theta is equal to theta, because theta is again very small, is equal to twice of h by r, is equal to this value, 1 minus sin square theta is equal to this value. Then theta is equal to d by twice of r. Now we have the value of sin theta, we have the value of cos theta. If we put these two values of sin theta and cos theta in this equation, cos theta over here and sin theta over here, we find fc square by f mu f square in terms of height of the ionosphere and radius of the earth is equal to this, where this d is nothing but the escape distance in case of curved earth scenario. So if we calculate this by doing some mathematical adjustments, we find that the escape distance is now became this. Escape distance is equal to twice of h plus d square upon 8r. This escape distance is the factor of escape distance itself. That is, this is the quadratic equation in d, where we get two values. One is imaginary values or impractical value, while another value is the practical value. So if we solve this quadratic equation, we can find the escape distance for the curved earth scenario over here with the help of this formula. Or by approximation, we can also write the escape distance is nothing but under root of 8h into r, where r is the radius of the earth and h is the height of the ionosphere. For approximate value, for exact value, we have to solve this quadratic equation for the curved earth scenario. Now the multi-hope skywave propagation. So as we already discussed that the ionosphere is made up of different layers of the different layers of the ionosphere, that is D, E, F1 and F2 layer, and for the different incident angle for the same wave at the same frequency get different reflection from the earth surface and reaches Rx. So this is known as single hope because there is no reflection from the earth over here. This is single hope scenario, but the wave is traveled 3 different individual paths. While in case of multi hope sky wave propagation, in which the earth is behave as a perfect conductor, and the wave from the wave from the transmitter is reflected from the ionosphere and reflected back from the transmitter as well, and reaches the another transmitter, that is point B, by multiple hoping. Like 2 hope is introduced over here. Another wave is going from with the help of single hope, and that another wave, the second wave is going by multiple hope. So you can also cover up the distance by multi hoping method or by single hoping method. But the problem is that for the curved earth and the traveling distance, the escape distance is very large. Even in the as the earth rotates, this terminator line is the line that differentiate daytime from the night time, and we also know that the daytime the concentration of the layer is different, and the night time the concentration of the layer is different. So this ionospheric layer get merged or distorted. So even if we are using multi-hope propagation, we are not able to reach to the point V, because in the half part the ionosphere layer is shifted due to the night time. There is very less concentration of electron. So by help of multiple hope, even we are not able to reach the receiver B over here. These are the characteristics of different layer of the ionosphere. For the D layer is the minimum layer with the height of 100 kilometer, and the maximum frequency, critical frequency, is 100 kilohertz. In case of E layer, this is 100 kilometer, and the critical frequency is 4 megahertz, and we can use in the single hope with the help of E layer 2350 kilometer we can easily cover, while in this case we can cover a very less distance of 70 kilometer over here. This is F2 layer, which is again above the E layer, and it covers up to 500 kilometer with maximum frequency of 5 megahertz. And the uppermost layer, that is F2 layer, cover 3800 kilometer, that is almost the two opposite point of the earth, and the maximum frequency is 12 megahertz. These are the different wave characteristics, like very low frequency wave, like 3 kilohertz to 30 kilohertz. It is not reflected by the ionosphere. Then these waves are reflected by the ionospheres, and there is some properties, like it is used in ground wave propagation up to 1000 kilometer, and the medium waves, that is used from up to 535 kilometer over here. This is again the medium wave, in which the maximum usable frequency lies, or optimal return is present over here in this range. This is the high frequency bands, and ultra high and super high, extremely high frequency band, and again sub-millimeter wave or optical wave over here. So these are some example with the help of different derivation we derived in this and previous lecture. We can do some small numericals with the derived formulas, like if we calculate the over here, we have to calculate the maximum effective aperture. So for this, the formula D is equal to 4 pi AE by lambda square we already derived. So you can solve this is the directivity, this is the operating wavelength. We can calculate the effective aperture of the antenna. For the critical frequency, it is 9 under root n max. For this, FC is nothing but 9 under root of n max. With the help of this formula, we can calculate this second numerical. Critical frequency is going to calculate the MUF. Then again we have the formula F MUF is equal to FC sec of I. I is the incident angle. Radiation resistance is given, or loss resistance is given. We can calculate the efficiency. Efficiency is nothing but radiation resistance upon radiation resistance plus loss resistance. And if we have the efficiency, we can calculate the directivity, which is nothing but gain is equal to eta times of directivity. we have eta from here. If we put eta over here, we can easily calculate the directivity. Directivity is nothing but gain divided by eta. And in this again we have to calculate the skip distance, for which the formula we already discussed in this lecture. So thank you for this lecture. This is the lecture over the skip distance. I hope many concept of the skip distance is cleared by this lecture.